So individual bonds have energies. There's energy associated in a bond. And what we call the bond energy is the amount of energy that's needed to break 1 mole of that sort of bond in the gas phase. So bond energies are always positive because you always have to put energy into the molecule to break its bonds. A stronger bond will take more energy to break, and so it will have a larger bond energy. We can use individual bond energies to estimate enthalpy changes for a reaction. So if we look at hydrogen chloride in the gas phase, this has a bond, a covalent bond between the hydrogen and the chlorine. And if we break that bond, we'll make 2 atoms, hydrogen atom and a chlorine atom. And delta H for this reaction is 431 kilojoules. And that is for the molar amounts given here, which would be 1 mole of bonds. So, I don't know where I was going with that sentence. Compounds that have strong bonds tend to be more stable. That kind of makes sense. And they're going to be less reactive because in order for them to react, their strong bonds have to be broken. And that requires energy to be put in to get the reaction going. And it takes more energy, and so it's going to be harder to get that reaction started. Bond energies are going to be slightly different in different compounds. Here we can look at the bond between carbon and hydrogen in several different molecules. So here we have methane, carbon bonded to 4 hydrogens. And if we break that carbon-hydrogen bond, it requires 438 kilojoules of energy. If we have trifluoromethane, where we've got 3 fluorines here, the bond energy goes up to 446. If we have tribromomethane, it's 402, and trichloromethane is 401. So we don't need to know these numbers or the pattern even, but just to be aware that the strength of that carbon-hydrogen bond is going to vary a little bit in different compounds. So instead of worrying about the exact energy in any given particular compound, we typically look at an average. So we say the average carbon-hydrogen bond is 414 kilojoules to break 1 mole of bonds. So we can look up these things in a table, average bond energies, and those have been calculated just using the bond energies in a large number of different compounds and averaging them together. As you can imagine, a double bond is going to be stronger than a single bond, and a triple bond is going to be stronger than a double bond, and so those will have even higher energies than the single bonds. So this is a table from chapter 9 of your textbook, and there's also a more expanded version in the appendix in the back. And so we can look up the bond energies here. Let's look at some of these carbon-carbon bonds. So here's a carbon-carbon single bond, 347, carbon-carbon double bond, 611, not quite double, but close. Carbon-carbon triple bond is significantly larger again, 837. There's one anomaly here that I want you to notice. The 736 has an asterisk. And down here it says 799 in CO2. So a carbon-oxygen double bond, the average bond energy is 736 kilojoules per mole, except in CO2. CO2 is a very common molecule, and the difference is pretty sizable here. So if you're using CO2, you have to go with the 799. But all the rest of these, you just read them off the chart. Well, how can we estimate enthalpy changes using bond energies? Well, if we break a bond, That's an endothermic process, right? So we just looked at that table. It tells us how much energy has to be put in to the molecule to break a bond. So energy is stored in that bond, and to get it out, we have to break the bond. What happens when a bond forms? There's an energy change, right? And so a bond forming is an exothermic process. It releases energy. So the way we can estimate an enthalpy change is we can add up all the bonds that are broken and all the bonds that are formed and figure out what the energy difference would be. So you can express it mathematically this way, that the heat of reaction is equal to delta H for the bonds broken, so those would be the bond energies, plus the heats, or the delta H's for the bonds formed. This is going to be negative. I tend to think of this, well, never mind. I don't want to go there. So let's look at how we might do this. And this takes advantage of this Born-Haber cycle here. Also is taking advantage of Hess's law. So here we've got methane and chlorine, and we're going to have these react. And they're going to form chloromethane and hydrogen chloride. In order for these to be formed, we have to take these molecules apart, right? So if you imagine these as being spherical Lego blocks, right? In order to make, to put an H and a Cl together, we're going to have to separate these two Cls. And so that's going to require energy. You have to put energy in, you have to expend energy to pull those apart. You're also going to have to pull one of the hydrogens off of the methane, and that's also going to require energy. So we can add up the bond energies for the carbon-hydrogen and the chlorine-chlorine bond and estimate how much energy is needed to break those bonds. Does that make sense? Then, when we put the chlorine with this hydrogen and we put this chlorine on the methane, or what's left of it, we are forming bonds, and that releases energy. And we can estimate that as well, because that's the bond energy with the sign changed. Conservation of energy tells us that you can't make or destroy energy just by making and breaking bonds. If you put 5 kilojoules in to break something, when that reforms, it's going to release the 5 kilojoules. So making the bonds is releasing energy, and the enthalpy of reaction is the sum of those two. The amount of energy needed to break bonds and the amount of energy released by forming bonds. Any questions? So we say that energy is stored in chemical bonds. I said that earlier. Breaking a chemical bond always requires energy. So an energy-rich compound can undergo a reaction in which weak bonds are broken and strong bonds are formed. It's the forming of the chemical bonds that releases energy. So when methane or propane burns, so you light up the gas grill in the backyard, as that propane burns, it releases a lot of heat. Where's that coming from? Well, you're burning something. Yeah, but why does that give off heat? Because the bonds between carbon and hydrogen and carbon in propane are fairly weak bonds. And you break those bonds, and then you form stronger bonds between hydrogen and oxygen, and double bonds between carbon and oxygen, making water and CO2. And when those stronger bonds are formed, energy is released, and that's where the energy comes from to cook your hamburger. So let's do an example. A potential future fuel is methanol. Write a balanced equation for the combustion of gaseous methanol and use bond energies to calculate the enthalpy of combustion of methanol in kilojoules per mole. So we have to write a chemical equation. So we've got our methanol, and when something combusts, what is the other reactant? Oxygen. So we got O2 here. And this is a compound containing only carbon, hydrogen, and oxygen. What are the two products? CO2 and H2O. And the H2O is going to be in the gas state because this is hot. So these are things that you should remember. Anything burning, combusting, oxygen is a reactant. It will often not be said. So it says methanol is combusting. Well, that we understand that means it's reacting with oxygen. When a compound containing carbon and hydrogen or carbon, hydrogen, and oxygen burns, it forms CO2 and H2O. And that's just another thing you need to remember. So now we need to balance this equation. So here we've got one carbon, and there I've got one carbon. And over here I've got 4 hydrogens, right? And over here I've only got 2. So I could put a 2 in front of water, and now I've got 4 hydrogens. Then I have to check out the oxygens. Over here I've got 2 oxygens and 1 oxygen, so that's a total of 3. And over here I've got 4 oxygens. So I need 1 more oxygen over here. This is the odd-even problem, right? I can't just put a 2 in front of the oxygen because that's going to give me 2 extras, and I only wanted 1. So what to do? Well, I could double everything, but I'm going to have to cut everything in half again later because we want to find the combustion in kilojoules per mole of methanol. So we'd really like this to have a coefficient of 1. So what I've got here on the left, I've got 1 oxygen and 2 oxygens. I can multiply this by something. I need 4. What can I multiply 2 by to get 3? It's a fraction. What if I multiply this by 3 halves? 3 halves times 2 is 3, right? So I can balance this using a fraction. Any questions? You don't have to do it that way, but this one is going to be messy enough that I really don't want to deal with it at the end. Okay, so use bond energies to calculate the enthalpy of combustion. So we could analyze this and figure out which of these bonds are broken, which ones remain intact, and which ones are formed. That involves a lot of thinking, in my opinion. What I find easier is to say, let's just take everything apart into atoms and then build from scratch at the end, and then we don't have to worry about, well, did this carbon-hydrogen bond stay or did it get broken? I think it's just easier. So think of Legos. What we're doing, instead of pulling the head off of this one and sticking it on that tree or something, just moving some, we're going to take the whole thing apart and build the new thing from scratch. Okay? So what we need to do is identify what are the bonds here. We need Lewis structures. So CH3OH. I'm not going to go over in detail the Lewis structure business here. But that's the Lewis structure for methanol. And for oxygen, it's going to look like this. On the other side, we're going to have CO2. And water. Those are their Lewis structures. So what I'm going to do is I'm going to figure out what kinds of bonds are being broken and how much energy that's absorbing, and I'm going to find out what kinds of bonds are being formed and figure out how much energy is released by that. So I first need to figure out, well, how many bonds of each kind do I have? So if I look at this methanol molecule, I have 3 carbon-hydrogen bonds, right, in that one molecule. So I have 3 carbon-hydrogen bonds. I have a carbon-oxygen single bond and an oxygen-hydrogen single bond. You see that? So I have 3 of these. Let's maybe highlight those. So I've got 1, 2, 3 of the carbon-hydrogen bonds. And then I've got a carbon-oxygen bond and an oxygen-hydrogen bond. I have 1 mole of those molecules, so I have 3 moles of carbon-hydrogen, 1 mole of carbon-oxygen, and 1 mole of oxygen-hydrogen. Down here in this oxygen molecule, I have an oxygen-oxygen double bond. So that's O double bond O. I don't have 1 mole of that molecule though. I have 3 halves, right? So that means I have 3 halves of a mole of these bonds. If you think of this in terms of molecules, you can't have 3 halves of a molecule. But you could have 3 halves of a dozen molecules. You can have 3 halves of a mole of molecules. So 3 halves of that one. Let's look at the products and what kinds of bonds are being formed. In carbon dioxide, I have 2 carbon-oxygen double bonds. And how many moles of carbon dioxide do I have? 1. So that means I have 2 moles of carbon-oxygen double bonds being formed. And this water molecule, I have oxygen-hydrogen single bond. There are 2 moles of those bonds in 1 mole of water. I have 2 moles of water. So I've got 4 moles of that bond. Yes? So how am I getting the numbers? That's an excellent question. So I'm looking at this molecule, and I'm going to say I'm making it from individual atoms. And so I have to figure out what bonds are being formed. So this bond is being formed, and that bond is being formed. So when I make 1 molecule of CO2, I make 2 bonds. If I make a mole of carbon dioxide, I make 2 moles of bonds. Right? Yeah. And in this balanced chemical equation, I've got 1 mole of CO2. Yeah. So I've got 2 moles of these sorts of bonds. Okay? Because in each molecule, there's 2 of the bonds. Right. So that's why there's 2. Yep. So we've got the carbon making a double bond with this oxygen, the same carbon making a double bond with the other oxygen. So every molecule that's formed forms 2 bonds. Similar things happening with the water. Each molecule is forming 2 of these bonds, but in my equation I have 2 moles of water molecules. So that means I'm forming twice as many. I'm forming 4 moles of bonds instead of just 2.
Are you multiplying it by 2?
Yeah, I'm multiplying it by 2. So we could think of it this way. I have 2 bonds per molecule, and I have where am I going with this? Well, if we think of the equation in terms of molecules instead of moles, there's 2 molecules that are being formed, right? So that would give me 4 bonds. But we're actually doing this in terms of moles. So this is 2 moles of bonds and a mole of molecules and 2 moles. We had an internet or Wi-Fi glitch. So what we're really talking about here is 2 moles of bonds per mole of molecules, and we have 2 moles of molecules that are being formed, so we have 4 moles of bonds that are being formed. Okay? It's an excellent question. So I'm going to erase that because I need the space. So we figured out what kinds of bonds we have and how many. And so now we need bond energies. So we don't remember these things, we go look them up. So I'm going to go back to this table. And I'm going to make use of the chalkboard because my short-term memory does not last that long. I do remember that we had carbon-oxygen double bond. It was the one in CO2 though. So that's 799. We also had, let's write it this way, an oxygen-hydrogen bond. That's listed there as a hydrogen-oxygen bond, same thing. 464. We had some carbon-hydrogen bonds. Hydrogen-carbon 414. And carbon-oxygen single bond 360. So I wrote those on the board so that now when I go back here, I can write them out. So here's our carbon-hydrogen bond, and from what we've got on the board, 414 kilojoules of energy. So we've got, that's per mole. So we've got 3 moles of that times the 414 kilojoules per mole. Okay, so then you do the math and you look at the units, the moles cancel out. Kilojoules per mole, and we do the math and they look at the units, and this is, the moles cancel out. So I'm going to leave the moles out of this because it gets very cluttered and congested here. I have 1 carbon-oxygen bond, 1 mole of them. So that's 360 moles. No, 360 kilojoules. And a mole of oxygen-hydrogen bonds, and that's 464 kilojoules. And then down here, I have 3/2 of a mole, 1.5 moles of the oxygen-oxygen double bond that I forgot to write on the board. So let's go back and look at that. Whoops. Oxygen-oxygen double bond, where'd you go? 498. So this is 498 kilojoules per mole. Well, I'll go ahead and write the units here. Per mole times 3/2 of a mole. So we can add up all the energy that needs to be put in to break all the bonds, take this whole thing apart. So get out the calculator. 3 times 414. 3 times 414 plus 360 plus 464 plus 3 divided by 2 times 498. I'm getting 2813. Anybody else get that number? Anybody else have a calculator? Well, check me in if it's okay. Thank you. So that's what we have to put in. Over here, these bonds are being formed, which means they're releasing energy. So I'm going to make this green then. So I've got 2 moles of carbon oxygen double bonds in CO2. So I look up that. 799 to break it, minus 799 if you make it. Okay? And then the oxygen-hydrogen bond, I have 4 moles of that, and that's going to be minus 464 kilojoules. The sign is opposite because I'm making the bonds instead of breaking them. It's like buying and selling stuff, right? One's positive, one's negative. Depends on your point of view, who you are. So 2 times negative 799 plus 4 times negative 464. So this adds up to minus 3454. So this is sort of like an investment. You have to contribute $2,813, but then after this is all done, you get back $3,454. Question?
How did you get 2,813 kilojoules? Because I did 414 times divided by 3, added 360, added 304, added 464, and then the 498. Am I multiplying that by
3 over 2. Yes. So this is times 3/2, or you can make it into a decimal if you want, 1.5.
So basically, if I do the math correctly, I should get that number.
Yes.
I think 3/2 is enough.
Yeah.
Thank you.
So overall, what we've got then is we're just going to add these two things together. So delta H is going to be 2813 kilojoules plus this negative number 3454 kilojoules. So negative 641. So for this reaction, delta H is estimated to be minus 641 kilojoules. So it wanted the enthalpy of combustion of methanol in kilojoules per mole. I calculated it for this balanced chemical equation, which is 1 mole of methanol, and so I can say that the units there are per mole. If we didn't use the fraction and had double of everything here, when we got to our number, it would end up being twice as large. And we'd divide by the number of moles, which was 2 moles, and it would come out to be the same answer, but all of these numbers would be twice as big.
Just divide by the moles of the methanol?
Yes. Because we want to know per mole of methanol what's happening. Any questions? A little tedious, but if you think about trying to set up the experiment to actually measure the enthalpy of combustion, doing the math then seems pretty simple in comparison. So a bond length is the average length of a bond between two particular atoms in a large number of compounds. So just like the bond energies are slightly different in different compounds, the bond lengths will be slightly different, but we can look at an average, and that's usually all we need. We find that double bonds are shorter, triple bonds are even shorter. So here comparing these three different bonds for carbon and carbon, single, double, and triple. We see that the triple is the shortest in length, the single is the longest, the triple bond is the strongest, and the single is the weakest, which makes sense. Here the carbons are sharing 6 electrons, and so that's going to pull them together. They're going to get closer, and because the attraction is bigger, then it also requires more energy to break them. We can say in general that longer bonds are weaker than shorter bonds, but that's just a generality. Here's some examples of bond lengths. Here with the oxygens, we see that a double bond is shorter than the single bond.